Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, find the minimum cost array permutation. The problem is actually hard and the video can get a bit longer, but if you stick till the end, I'm very sure you will be able to learn few new things from the video that you can apply generically across different set of problems that you might encounter in future. So with that, let's get started. The problem states that you are given an array nums, which is a permutation of 0 to n minus 1. The score of any permutation is defined as this particular expression. You have to return the permutation which has the minimum possible score. And if there are multiple of them, you have to return the lexicographically smallest one, right? So let's take an example. Let's say nums is 102. This is the permutation that is given to us, and we need to return a permutation that will minimize this particular expression. So one of the permutation that would minimize this expression would be 012. And what would be the minimum value? Minimum value would be perm of 0, which is 0, minus nums of perm of 1, which is nums of 1, which in this case is 0. So 0 minus 0, which is 0. Then second expression is perm of 1 minus nums of perm of 2. So perm of 1, which is 1, and nums of perm of 2, which is 2. So 1 minus 2 modulus, which is 1. Similarly, the last one would simply be 2 minus 1 modulus, which is equals to 1. So the cost of this particular permutation, or the score of this particular permutation, will be 2. And you can try out any other possible permutation. You will not be able to get a cost lower than 2, and even for other permutations which have a cost of 2, this is the lexicographically smallest one, and hence this is the answer, right? So hope the problem statement is clear. Now, what is the brute force way to solve this problem? One of the brute force way would be like you will simply try out every possible permutation and figure out the score based on this expression, and whichever permutation gives you the minimum score, you will simply keep that as an answer. And if there are multiple of them, you will simply keep the one which is the lexicographically smallest one. So in this particular example, these two permutation will give you exactly same score and the minimal score with this nums array, but among these two you will keep this one because this is the lexicographically smallest one. So if you don't know about how to create all possible permutation of an array, this could be a nice problem to try that on. You can write a simple recursion that will give you all possible permutation of a given array, and for each of them you can simply find the score and keep the one which is the smallest. So overall complexity of that approach would be order n factorial, because there is n factorial number of permutations, and for each you will be figuring out score that will take you order n time in minimal scenario, because you will be iterating over every element at least once. So this is the overall time complexity of your approach. The value of n in this problem is very small, so but even 14 factorial is very huge to fit in the given time constraint. So this solution needs to be optimized. Now, what does this mean? This means that you can't afford having all possible permutation, or you can't afford going over all possible permutation. You need to think of something smarter, right? Now here comes the harder part. You need to now think of ways to give the permutation without iterating over all of them, right? So one of the approach here is, okay, let's not worry about permutation, let's just focus on figuring out minimum possible score. And if we are able to figure that out, we can traverse backwards to figure out the permutation which give us minimum possible score. Again, if you don't know about how to traverse backwards to get the actual permutation, that's fine. We'll come to that, but the motive for now is to figure out minimum possible score, not the exact permutation, right? So we want the permutation which gives us the minimum possible score, and we don't want exact permutation, we just want the score. And even in that, let's simplify it even one step further. Let's say the cost function for now is not perm of 0 minus nums of perm of 1, instead perm of 0 minus nums of perm of 0, perm of 1 minus nums of perm of 1, and so on and so forth. Basically, intermixing of indexes will lead to certain complexity, which we will see later. So for now, what we have done, we have simply keep each indexes separate. So the first expression just works with index 0, and similarly second one and third one, and so on and so forth. So this is our new cost function. We need to minimize the total score, and we don't want to iterate over all possible permutations. So if we don't want to iterate over all possible permutation, or rather if we don't want to have n factorial in our time complexity, it inherently means that you can't store n different, like the values of all n different boxes at a single time or in every state. So somehow you need to avoid keeping the previous state while computing the next state. That's the basic trick. So let's look at it. Let's say you want to fill something here, right? So what are the possible choices? You have total 6 elements, 0, 1, 2, 3, 4, 5. Among these 6, you will pick one of them. So let's say you pick for now 2, right? Now what you have remaining with, you have this entire array, and you need to fill this entire array with 0, 1, 3, 4 and 5 such that the score is minimum possible. And note that the score doesn't interact with anything that has happened in the past, because we have already separated the indexes completely. So whatever has happened at index 0 doesn't matter for rest of the indexes, and because that's the case, you can treat the rest of the array as an independent array and solve it independently. So the original problem was, given 6 numbers 0, 1, 2, 3, 4, 5, you have to fill these 6 boxes such that the score is minimum possible. Now the problem is, you have fixed one of the indexes here, so you know that you have to fill the remaining 5 boxes with remaining 5 elements such that the score is minimum possible. So isn't this problem exactly equals to the original problem? Original problem was, given some numbers, you have to fill those such that the score is minimum. The new problem is, again, given some numbers this times are less in count, because previously we have 6 numbers, now we have 5 numbers, and we have to arrange these numbers such that the score is minimum possible. So both the problem are exactly similar. So hope you can see the recursion here. You can define a simple function, let's say, that takes in an array, and let's say this takes in the index you are working at. So what you want is, you want to arrange all these numbers in this array for everything starting at index I, such that the arrangement gives the minimum possible score. So at this state, what you can say is, okay, what I want to fill at the ith position, or what are the possible choices of ith position. Possible choices of the ith position will be one of the element from this array, right? So let's say this array has 3 elements. So this index I has 3 possible choices, right? One the first element, then the second element, then the third element. Based on what you put, you will simply say that, okay, let's say you have put 2 here. This array, let's say, had 0, 1, 2, 3, 4, 5. Now you put 2 here. So if you have put 2 here, what you want is, you want to fill the rest of the array starting at index I plus 1, and you are remaining with an array which is not containing 2, because 2 is something you have already filled. Similarly, if let's say you have filled 3 here instead, you would want to fill the rest of the array with elements from this array, where this array will not contain 3, because 3 is something you have already filled, right? So that's the overall trick. So let's look at it in a formal way. Let's get rid of this. So we have this f of 0 comma array, which denotes what all we have, right? Now at the current position, or rather at the ith position, we can fill any of these, right? So we can either fill 0, we can either fill 1, we can fill 2, we can fill 3, 4 or 5. Based on what we fill, we need to now fill the rest of the array such that I will get minimum cost from the remaining set of elements. So if you filled 0 here, you only have 1, 2, 3, 4 and 5 to fill starting at index 1. Similarly, if you filled 1 here, you have 0, 2, 3, 4 and 5 to fill starting at index 1, and so on and so forth. Now based on what you fill, you can figure out the contribution of that particular expression. So if you have filled, let's say, 0 here, you can compute this particular expression, because perm of 0 is 0. So 0 minus nums of 0, which is 0 minus 0, which is 0. So what you're saying is, from this particular number I got a cost of 0, and now I want to fill the rest of the array such that I got the minimum cost. So this is the total cost if you fill the first position as 0. Similarly, if you fill the first position as 1, let's say you instead of 3 you have put 1 here. So in this case the cost would be 1 minus nums of 1, which is 1 minus 2 modulus, which is 1. So in that case the cost would have been 1 plus whatever is the cost to fill the rest of the, whatever is the minimum cost to fill the rest of the elements. Similarly, if you fill 2 here, then the cost would be 2 minus nums of 2, which is 2 minus 1, again 1. So 1 plus this, which denotes the cost to fill the rest of the elements with everything except 2, right? In the same fashion, you can figure out all possible cost, right, and just take minimum across all of them, and that will give you the minimum possible cost to fill the entire array with 0, 1, 2, 3, 4, 5 starting at index 0, right? So this is like the overall algorithm. Now what is the pseudocode? The pseudocode would look something like this. Whatever we just discussed, we will simply have this array available, which will denote what is the available elements to fill, and an index which denotes like which index to start filling the values from. Now if index is n, which basically means we have filled all the elements, so there is nothing to fill, and hence the remaining cost is simply 0, right? Otherwise we, like, this is, we'll come to that now. Otherwise what we'll do, we'll simply try filling up all possible values at the current index. So if we fill, let's say, I here, the current cost would simply be I minus nums of I, and this will say this is the cost of filling I here. Now I want to get the minimum cost to fill the rest of the elements in the rest of the spaces. So basically you want f of available except I, and you want to fill all the elements starting at index plus 1, right? So you want the minimum cost to fill all these elements, so that will give this f will give you that, and from all such I you will simply take minimum across all such I to get what is the minimum cost to fill all these different elements starting at this particular index. right? And one important thing to note here is you might encounter same state again and again, because you can think of like you have filled, let's say, 0 first and then you have filled 1 first. So what you want is you want to fill the rest of the elements with 2, 3, 4 and 5, right? Now let's say you filled 1 first and then 0. Now what do you want? You want to fill the rest of the elements with 2, 3, 4 and 5. So these two are exactly the same state and you don't want to compute both of them again and again. So first time you compute it, you will just save it somewhere, and then next time when you are asked for computing the exact same state, you can simply look up and return that as an answer. So to save on that computation, we are simply memorizing it with this dp variable. Now, what is the overall time complexity of this algorithm? The time complexity is simply number of states multiplied by what you are doing inside each of the state. So number of state is simply number of different values of this available multiplied by index, and we'll come to that. Let's figure out what we are doing inside each of the state. So first of all, we are computing each state exactly once, because if it is recomputed or if it is asked again, we will simply return from here, because it is guaranteed that we will have this value and we will return it. So we will be computing each state exactly once. Now what we are doing for each of the state, we are simply iterating over all the available elements here, and in worst case it can be order n. So we are simply doing order n operation inside this function to figure out the value of a single state. Now how many states are there? This is interesting. So in first look, it might look to you that okay, number of states is n factorial, because there are n numbers and you can arrange it in any fashion you want, but that's not true. Number of states is actually 2 power n. How? I would encourage you to pause and try to think by yourself. There are multiple possible ways to arrive at 2 power n. Let's discuss two different ways, one through mathematics and second through intuition. So what is available? Available is an array which contain what all elements we need to fill or we can fill in. Now number of elements here matters, but their order doesn't matter. Like if you are said that you have to fill 0, 1, 2, 3, 4, 5 and you are said that okay, you have to fill 1, 0, 2, 3, 4, 5, both of them are exactly similar, so order doesn't matter. So that's where like n factorial is surely not the case, because the ordering doesn't matter. Now in simple words, what you are doing is combination instead of permutation. So you are saying that at first layer you will have all the n elements, then at second layer you will have n minus elements, n minus 1 elements, at third layer you will have n minus 2 elements. Basically when you expand this thing, because to even compute this f of 1 comma 1, 2, 3, 4, 5, you need to first fill in the position 1, and to fill in position 1 you will have this 5 ways, and you will expand this further in 5 different branches, and so does for this as well. So in this third layer we will have this available element will have 4 elements, because available array will have 4 elements because you have already filled 2 of them. Similarly at fourth layer available will have 3 elements, and so on and so forth. So at first layer you have n elements, so you total have n elements, and what are the different possible ways to have n elements or to choose n elements from n elements, which is NCN, right? Now at second layer you have n minus 1 element, so number of different ways to choose n minus 1 elements from n elements is NCN minus 1. Similarly at third layer it would be NCN minus 2, and so on and so forth. So overall, if you sum this entire thing up, you will be having 2 power n distinct combinations. So overall number of states or overall number of different values of available would simply be 2 power n, right? So if this was a bit hard, let's try to look at it in a different angle. Instead of saying what all is available, you can instead say whether a index is available or not, right? You have 6 different integers, 0 1 2 3 4 5. You can represent a boolean for each of these variables, right? And you can say if it is 1, it means it is available. If it is 0, it is not available. So initially everything is available. Now when you pick 0, 0 is not available, rest are available. When you pick 1, 1 is not available, rest are available. When you pick 2, 2 is not available and rest are available, and so on and so forth. So in this fashion, you are maintaining a boolean array of size n. Now what are the total different possible states of this boolean array? It will be 2 power n as well. So like we just saw that we just saw 2 different ways to come to the conclusion that number of different states that a variable could have is 2 power n. Now 2 power n multiplied by number of different values for index, which is n. So number of states is n multiplied by 2 power n, and the overall complexity would be n square multiplied by 2 power n, right? Now this is sufficient to pass the given time constraint, but we can easily optimize this. How? We can easily remove this index. How or why is something I would encourage you to pause and try to think by yourself. So hope you thought about it. Basically this index is something which we can derive from the available array itself. So assume that available is this, right? So in this case, what is the index you are looking at? Index would simply be n minus count of ones, right? I think I mistakenly written count of ones, but it will be n minus count of ones. Or if available array looks something like this, then it will simply be n minus available dot size, right? So index is something which you can derive from available itself. So there is no need to maintain index in your DP state as well, or in your recursive state as well. You can simply derive this index from the available itself inside this function itself. So your number of inputs to the function has reduced, and hence complexity would also be reduced. So number of different states now is 2 power n, and what you are doing inside each of the state is still order n operation. So complexity is now order n multiplied by 2 power n instead of n square multiplied by 2 power n, right? So if you haven't understand until this point, I would strongly encourage you to rewind and make sure you understand up till this part, because the next part will be a bit more tricky and we will build on top of this. So let's now focus on the original problem itself. So original problem, if you remember, had this particular cost expression, which is perm of 0 minus nums of perm of 1, perm of 1 minus nums of perm of 2, and so on and so forth. Basically each expression involves 2 adjacent indexes, and the last expression involves the first and the last indexes, instead of each expression having just 1 index. Now if you understand the previous part, it's the right time to pause and think about how you will approach this particular piece. It's something we have done multiple times in this channel, so if you have been following, you might be able to crack it as well. So notice what will not be applicable that we have discussed before. So this was the previous solution, and in this we had this current score as I minus nums of I plus f of available dot remove I, basically everything except I. Now this part was something we were computing for this particular expression, or the ith expression in this entire expression. But now to compute current score, you need 2 different values, right? Let's say you are at ith index, you would need ith index and I plus 1th index, and then only you will be able to compute this particular expression, right? So at ith index you want to have I minus 1th index as the value of I minus 1th index as well, because otherwise you can't compute this expression at all, right? So that's what basically what you can do is you can simply maintain previous value as well while going forward. So when we are going forward, we just have this information that what all elements are left. Now along with what all elements are left, you can also maintain what was the previous element, and that is very simple to maintain. You can simply pass in I from here, because I is the last element that you have filled. So in the next state, I will be the previous element of the next state. So you can simply maintain one previous element, and once you have done this, this expression is something which you can compute easily. This expression would simply be previous element minus nums of I, or rather nums of previous element minus nums of I. Now notice this slight change as well. Currently, to compute even the first expression, you need the first and the second element. So you can't compute the first expression until you have fixed the second element itself. So currently what you will do, you will compute this score for the first expression at index 2, right? Whenever index is 2, you will compute this first expression. Now whenever index is 3, you will compute this second expression, because at index 3 you will have this particular thing, and with previous you will have this perm of 1 as well. Similarly with index 4 you will compute this, and so on and so forth. So basically you will be computing expressions, the previous expression in the current iteration, right? So at 0th iteration you will not have any expression at all, because at 0th iteration you just have perm of 0, and perm of 0 can't be used to compute any value. So at 0th iteration you will not compute anything. At first iteration you will compute this based on what you have put at the 0th iteration. So this will be computed at the first iteration, second, third, fourth and fifth. Now after 5th iteration you are still left to compute this thing, and to compute this thing you need the current value which you have, because you are currently filling up the 5th index itself or the 6th index itself, and you need the first element now, because nums of perm of 0 would basically means the first element. Now you have this perm of 5, but you don't have perm of 0, because you are just printing the previous element. So you have perm of 4 and perm of 5 with you at the current instant. You don't have perm of 0, but you need perm of 0, right? So that's also something you need to carry over to your next state, because that is something which you will need in the last to compute the last expression when you are filling up the last state, right? So at this state you now need three things. One, the previous element. Second, what all elements are left. So in this particular scenario 3 and 4 are left, right? And third, what is the first element that you have filled in this entire current permutation, which is 0. So you maintain begin, previous and available. So this will be your new state. Again, to maintain begin you can simply pass in one more value, because begin will simply be begin if it is not 0. If it is 0, then whatever is the value of I is the beginning that you are doing with, right? So this will be your total state. Now let's look at the pseudo code. The pseudo code would exactly be similar, just a few changes here and there. We have three things in our state: available, previous and begin. And inside this we'll come to this base cases sometime afterwards. Inside this what we are doing is exactly same. We are simply iterating over all possible available elements, and for each of these available elements we are figuring out the score, or rather the expression that we have been given. So let's copy over this and let's see how we are dealing with this. So here you can see at index 0, when index will be 0, again this will be count of zeros or n minus count of ones, whatever you call it. At index 0 you are picking up what to fill at first position, right? So you have this array which have 6 different spaces. So at index 0 you are picking up what to fill here, and with this you can't even compute the first expression, right? So at index 0 you will not have any expression at all, so you will only compute this at index greater than 0. So at index 0 you will not have any expression computed, right? Now this will come to that, and what you want, let's say you filled 3 here, assume that. So if you fill 3 here, you want to fill the rest of the element with the remaining set of elements such that the score is minimum possible, and you know that the first element in this entire array is something which you have just filled, which is 3. So basically if index is 0, then whatever you have filled here is the first element. Otherwise, if index is not 0, let's say you were filling up this index, then whatever was begin will be your first element, because begin is not changing at current instant, right? So we'll come to that. So let's say at index 0 you got a new begin. So when you will be calling the next iteration, you will simply say I have been left with these all elements. The previous element that I have filled is I, and the first element in this entire sequence is new begin, or in other case it would be I as well, right? Now based on this score, you can simply compute the min score, and that will you will do this for across all possible first set of elements. Now let's talk about some random ith index. So at ith index, what you have what all elements are remaining to be filled, right? What is the previous element and what is the first element, right? So let's say now you pick one of these indexes. Let's say you pick 5 here. 5 was there somewhere here, so you picked 5 here for now. So what you will be able to compute, you will be able to compute the second expression here, or I minus 1th expression here, and the value for that would simply be whatever was the previous value. Let's call it 1 for example. So whatever was the previous value, in this case 1, so 1 minus nums of 5 is something which will be the value of the current expression, right? And what you want to now fill, you want to fill the rest of the indexes with the rest of the elements, which in this case is you are left with 0, 4 and 2. So you will say I am left with 0, 4 and 2. The previous element that I have filled is 5, that's the element, and the beginning of this entire array is still 3. That doesn't change, right, at this state, because that is something you have filled at the beginning and that is constant. So beginning is still 3. So that's where this new begin says that if index is 0, then only we will assign a new value. Otherwise, whatever is the beginning, that will stay, that will remain beginning, right? And finally, let's look at the last index, right? So let's say you have filled this with 2 and here 0. Now there's just one element to fill here, which is 4, right? So you are now filling this in this thing with 4, and at this state what you have is, let's just get rid of this. So at this state what you have is what to fill, which is 4, what is the previous element, which is 0, right? And what is the first element, which is 3. That's what you have. Now at this state you will be computing this thing first of all, which is perm of 4, which is 0, minus nums of perm of 5, which is nums of 4, right? Now once you compute this, you also need to compute this at this instant only, because that's the last iteration you are doing. So you want complete sum, right? So at this iteration, you will also compute this expression, which is simply nums of perm of 5, which you already know, which is 4, right, minus nums of perm of 0, which you already know is 3. So num 4 minus nums of 3 is what you will compute, and that's what this second current score is denoting. Basically, if index is the last index, you will compute, you will have one more score to deal with, right? Now, based on whatever is the current score will be based on what you have chosen at this index, and how to best arrange the rest of the elements in the rest of the indexes, and you will simply take minimum across all possible first value, and that will give you the minimum score to fill all the indexes starting at this particular index, such that you are only having these all elements, and this is the previous element and this is the beginning element, right? Now the base case will still remain the same. This index is equals to n. If we have filled everything, we simply return 0. One thing which is changed now is because there is more state or more things we are maintaining with the next iterations, we need to capture them as well while computing or while persisting our state. Because when someone asks, okay, I need to fill 3 4 5, so give me what is the minimum score possible, so this is not enough information to judge, because 3 4 5 can occur when the previous element is either 0 2 or 1. So you also need what is the previous element, and you also need what was the first element, because if 0 is the previous element, first element could be 1 or 2. You need what is the first element, what is the previous element, and what all things are left to actually calculate the state. So in this scenario, you are computing all these three things, or you are maintaining all these three things in your DP state as well, right? So what is the overall time complexity of the entire algorithm? First of all, number of states multiplied by what you are doing inside each of the state. Inside the state, you are still doing order n operation, because you are just iterating over this available array. So you are doing order n operation inside each of the state, and because of this DP, you will be computing each state exactly once. So you'll simply need to take this entire thing into account only once for each state. Now, how many states are there? Number of distinct values of available, which is 2 power n. We have seen that in the past. Previous number of distinct value of previous, again, it can be anything between 0 and n, so it is again n distinct values. Number of distinct value of begin, again n, it can be anything between 0 and n. So overall state is n square into 2 power n, and you are doing order n operation inside each of the state. So overall complexity is simply n cube multiplied by 2 power n, right? And this is also okay for the given constraint where n is actually very small, n is 14, so even this would pass the given time constraint. But there is a way to optimize this by doing some observation. Now the next observation we are talking about, or we will be talking about, is something which is optional for this problem, because this solution will definitely be within the given time constraint. So, and the next observation is actually a bit trickier as well, because it's not very intuitive to come up with that observation during the contest. Even I was not able to do that, and I looked at that after the contest when I was looking at some of the different solutions. So the next observation is basically the fact that the given expression is symmetric across or given expression doesn't depend on the actual elements, it only depends on the order of the elements. What I mean, remember this example from the very beginning of this video. We have this permutation given to us, and these two will give us the minimum value, and these two are simply a rotation of each other. So you can get this array by simply rotating this array at index 3. So you can simply rotate this to twice in the clockwise direction and you will get this particular array, and both this array will have the same score. Why? Because of how this entire thing this entire formula of cost is built. You have perm of 0 and you have perm of 1. So basically the first expression just depends on first and the second element, second expression depends on the second and the third element, or rather every expression just depend on the next element. So as long as the relative ordering are same, it doesn't matter what is the beginning of the array or what is the ending of the array, the cost would come out as equal. So even if you don't understand right now, let's look at one of the example. Let's try to figure out the cost for this particular permutation. So in this case, the cost would simply be perm of 0 minus nums of perm of 1, which in this case is 2. So perm of 1 is 2. So basically the cost would simply be 0 minus nums of 2. Similarly, next expression is perm of 1 minus nums of perm of 2. The perm of 1 is 2, nums of perm of 2 would simply be nums of 4, and so on and so forth. And let's figure out the cost in the same fashion for this one as well. Now look at the expressions. 0 minus nums of 2 is actually exist here as well. 2 minus nums of 4 also exist here, right? And 4 minus nums of 5 also exist here, and 5 minus nums of 3 also exist here, and 3 minus nums of 1 exist here, and 1 minus nums of 0 exist here. And notice the symmetric behavior, like these all are adjacent because the numbers are actually adjacent. So this kind of proves that if the relative ordering is same, it doesn't matter what is the actual first or the last element, or what is the indexes of the elements, the final score would be equal. Now because of this property, we can say that we can always start with value 0, because we wanted the lexicographically smallest permutation. So we can always start with value 0. That's the best thing to do, because that will be the smallest permutation of this particular arrangement, right? So in this case, we kind of assumes that the first element would be 0, or it is actually possible to get an array where the first element is 0. So instead of trying out all possible beginning, we can simply assume that the beginning will always be 0 and we will only fill everything starting at index 1. So we don't need to maintain begin, because the assumption is begin is always 0. So begin, we can simply put 0 here, and this begin is something we don't need to carry over. And because this begin is something we don't need to carry over, this n will also go away, and this complexity would then become n square 2 power n, which is better than the previous one, right? So again, this part was tricky. This is actually difficult to get during the contest, but this is a nice optimization to make it order n square into 2 power n. So next we'll be looking at the code. The code will be looking for n cube 2 power n itself. N square 2 power n is something you can do by yourself. You know how to remove indexes. We have seen that just before while optimizing one of the solutions, right? So we will be looking at the code, but before that, we haven't yet solved the entire problem yet. We just figured out what is the minimum possible score, but the original problem asks us what is the permutation. So figuring out what is the permutation is something which is simpler now, because you know what is the path. Like you know the minimum score, you just want to know what is the path that lead you to the minimum score. And figuring out path from this is actually a very straightforward problem. Like you might have solved similar things in the past, like what is the longest increasing subsequence, enumerate the longest increasing subsequence or stuff like that with DP. Basically what you are saying is, apart from just maintaining this minimum score, you will also maintain what is the next state that gets you this minimum score. So here you know that you are doing minimum across all possible values of I. So instead of just doing minimum, you will also maintain one more variable. Let's say let's call it path. So you will also maintain a path variable. Again, this path variable will be per state, which is available, previous, and begin. So for each of these state, uh, or for this particular state, you will maintain all the different state that you get to. So let's say some I, let's say 4 has given you the minimum across all possible available. So you will simply maintain that okay, 4 is something that is given me the minimum possible value, and also begin was this, let's say X at that state. So you will maintain these two things. Now when you start, you know that you have started with everything available, like this is entire array, and begin and previous was kind of some dummy values, right? Now from here you know what was the state that you have taken in the minimum route, right? Because you have stored that already here, right? So from here you know what is the previous element that you have put. So you know this particular value, and you know this begin value as well. So you can simply remove this previous value from this and you will get this array as well, or you can, if you want, you can store this array as well for simplicity. That's up to you. So from this you will get to the next state, from this again you will get to the next state, and so on and so forth, and you will simply keep on collecting these previous values, and that will give you this entire permutation, right? Again, if you don't understand this, that's fine. That's not the hard part of the problem. Hard part of the problem is to come up with this particular recursive function, and if you are able to understand this, I think your motive of upsolving is satisfied. You can simply code this entire thing and compare your code with one of the correct solutions to understand whether you have coded it correctly or not. Coming to how to enumerate the path, you can take it up as separately. That's a very standard problem, and if you understand this, I think that understanding that would be a very simple thing. So next we're looking at the code, but as always, if you know how to figure out the path, I would strongly encourage you to pause and try to code this entire thing by yourself before moving forward. So the code is exactly what we discussed. Again, I have coded the n cube 2 power n solution instead of n square 2 power n. So we have available, previous, and begin at the state, right? One more thing is something you are noticing, that instead of an array I have a integer y. That is something which is very standard in these kind of situations. You can see that this is a boolean array, right? And number of element in this array would be less than equals to 14, right? So you have like 14 such ones and zeros, right, at max, and an integer has 32 bits, right? So if you like make if you represent an integer in its binary format, it can have 32 bits in total, right? Or basically 32 ones and zeros. So what we are saying is, let's convert this to an integer, because it will be possible, because there is just 14 of them and integer has 32 of them, so it will be possible. So let's convert this to integer, so that while maintaining this DP, we don't need to maintain a array or a map of DP. That would actually make lookup complex and might increase the time complexity as well. So whenever you see these zeros and ones, more often than not, you will be converting this to a single integer if possible, and using that to memorize instead of memorizing with this raw array, right? So that's what we have done. We simply converted this into a integer. Again, if you face difficulty in doing that, if you don't understand bit mask, there are a lot of videos in this channel, you can watch that. And for the purpose of this solution, you can still work with this array. It's just that this dp array would not be an integer, rather it will then become a map, and similarly this path array as well. So what we are doing, we are simply setting up few variables and figuring out the min score of 0 0 0. Basically first 0 denotes the beginning element, second 0 denotes the previous element, and third 0 denotes that what have we taken, or rather this entire array. So this is 0, which means that everything is 0, you have not taken anything, right? So instead of available, we are maintaining what we have taken, just same thing with just the opposite part, right? So initially this 0 0 doesn't denote anything because this mask is 0. Basically you haven't assigned anything to the first element itself, so this 0 0 doesn't mean anything as of now. So inside this, we'll simply check if this is the last index. Again, you can either do this, or you can also compute this index as we have been showing here. So you can do this, compute this index, or you can simply work with mask. So if everything is set, that means everything has been assigned to every indexes, so you will simply return 0. Otherwise, you will check your cache. If it is something you have already computed, you will simply return it from the memory. Otherwise, you will iterate over all possible available indexes. Now notice that this is a Boolean matrix, so you will iterate over everything, but some of them will not be available, right? So you will simply have to ignore them because those are already assigned. So this is like the standard way to ignore them. Again, here you can convert this mask to a Boolean array if you don't understand this, but this is a simple way to check whether a bit is set or not, right? So this is saying that whether ith bit is 1 or not. If it is 1, it means it is already taken, so I will simply continue, right? After that, we are computing the value. The value will compute by saying that whether it is the first element. If it is the first element, I will not be able to figure out any expression at all, so I will simply use 0. Otherwise, I know what is the value of the expression because I know the previous value and I know the current value as well. So current value is I, so the value would be simply be array I minus previous, or previous minus array I, however you call it, because of absolute both of them are symmetric. Now after that, if it is the last element, then you need to have one more thing to add, which is the value of the last set. So if it is the last element, you need to add this one as well. So that you will figure out via array of begin, right? And finally, this is your current value, or rather the value of the expression by putting I at the current position. Now you want to put rest of the indexes in rest of the positions, so you will simply say that I have used I, so you will set the ith bit, and the previous element that I have used is I, and the initial beginning was this new begin. This new begin, again you will change if it is the first element, because if it is the first element, then I is the something that you are assigning first. If it is not the first element, you will simply use whatever was the first element that this state was, that this state knows about, right? So you will simply add that score as well to val. So this is the total score. This val contains the total score of filling up everything starting at some index such that the previous element is this and the beginning element is this, and you are only allowed to fill some of the indexes which is represented by this mask. Now notice you also need to first of all you need the minimum value, so you will simply check whether it is less than answer or not. If answer is already lesser, this value is the greater one, so it doesn't make sense to put I at the current index, right? Now if it is less than answer, then it makes sense to put I at the current index, because that is yielding lesser score. Now if that's the case, you want to do two things. First, reassign your answer. Second, you also want to assign your path, because path will tell you which state you are coming from. So this will say I get the minimum value by assigning I to the current position, and in the beginning element was this new begin itself, right? Now if you do this entire recursion and this recursion ends, where min score of 0, 0, 0 will tell you what is the minimum score to assign everything starting at index 0 with everything from 0 to n minus 1, right? Now you want exact permutation. So you know the starting state was 0, 0, 0. Now you will simply iterate over the path and get to your next states. So you know that from this state, like from this begin, prev and mask, this particular state, you will, the best move forward was this, that you know. So basically you know what was the best move forward, so that will be your current element, and you will simply move that step forward. And this, I have not put mask here, so I just computed the mask based on the previous, because that's how it is computed. So if this, once this loop ends, result of j will have all the permutation, and you'll simply return that result, right? So hope this entire solution is clear. If you have any doubts in any of the piece, feel free to follow up in the comment section below. I would be happy to answer. I hope you are able to learn at least one new thing from the video. If you do share it with your friends so that they can also benefit from it. With that, I will see you in the next one. Thank you.